So it's my pleasure to introduce colleague and friend Zheng Zhang from Shanghai Tech in Shanghai. It's a new university with a very dynamic group of geometers. He's going to give a talk on the modular space of cubic surface pairs via the intermediate Jacobians of Eckart cubic threefolds, and it's joint work with Sebastian, Casalain, and Martin. Okay, so it's up to you. And he cannot have the camera on because of connection issues, but I think it should be okay.
Yeah. Okay, yeah, thank you very much, Jesus, for the invitation. It's a great pleasure to talk here. This will be a talk on some report on a joint work with Yano, as Jesus was saying, on this modular space of cubic surface pairs. So let me first give the overview. So the object we are interested in are these cubic surface pairs. By that I mean S is a smooth cubic surface, and the pi is a plane, transverse plane in P3 meeting this S transversely. So then we try to study this cubic surface pair, basically using Hodge theory. And what we do is, of course, there is no standard way to to associate some Hodge structure to this cubic surface pair. So what we do is we first do some geometric construction. So we get something, some cubic threefold X, and so this cubic threefold X has some special geometric properties. So we call it Eckart cubic threefold. So in particular, this X admits some involution tau. Okay, so then we look at like the most important Hodge theoretical invariant for cubic threefold, which is an intermediate Jacobian of this cubic threefold. So for curves, we have the Jacobian, then we have the Torelli. For cubic threefold, we also have this intermediate Jacobian, which is a PPAV, principally polarized abelian variety, on the third cohomology group of this X. Okay, and then I mean we study like what happens with respect to this involution. We found that because we have this involution tau, so this intermediate Jacobian splits into two parts: invariant part and the anti-invariant part. And this anti-invariant part we denote by Jx negative tau. So it's a more interesting one. The first result of our first result is that this anti-invariant part of this intermediate Jacobian determines this cubic surface pair. That's a Torelli theory. And like the key ingredient for proving this is that we realize this anti-invariant part, this Jx negative tau, can be realized as a prime. And later I will explain. But the corresponding prime map is this P34, which basically so this R34 are some double covers of genus 3 curves branch at 4 points. Then you take the prime, you get some abelian fourfold, and that abelian fourfold has a polarization of this type of 1, 1, 1, 2. Okay, okay, and this anti-invariant part basically lives in this A41112, and we prove that the fiber of this prime map is this S-intersect pi, which is an elliptic curve. But anyway, I will come to it later. And that turns out to be that's our second result. This fiber of the prime map, which turns out to be the key ingredient for proving the Torelli theory. Okay, so that's an overview. And so then let me go to some details. Okay, so as I said, so the basic object of study for us is this cubic surface pairs, where S is a smooth cubic surface and pi is a transverse plane. So they so this S and pi meets along a smooth elliptic curve. Okay, and there are some motivations for studying them. For example, this S S intersect pi. So they gave a log Calabi-Yau, and some people have studied this log Calabi-Yau from a perspective of mirror symmetry. And also this one is an interesting example for studying log K stability. So here let me mention the work by Patricio Jesus and Spaldi. So I think they studied like the variational GIT for these cubic surface pairs, and also use the variational GIT to study some some problems on log K stability. And also another motivation for me is that joint with Radulada and Greg Pelstein, sorry, there's a typo. We have studied these cubic threefold pairs and studied construct a period map and study the corresponding moduli. Okay, so next maybe let me quickly recall the work I did with Radu and Greg. Okay, so here the difference is that the dimension is one dimension here. So here we are starting some cubic threefold pairs. So namely it's X, H, where X is a smooth cubic threefold and H is a transverse hyperplane in P4. So then let's assume that the equation of X is given by this F, and the equation of H is given by some linear form L equals 0. So then what we do to construct the period map for such a pair is to first encode this pair X, H as a cubic fourfold. Okay, so the equation is very explicit. So so it's just F plus L times a new variable squared. So X5 squared equals 0. So clearly this is a cubic fourfold. It's smooth. And so just directly from this equation, you can see some geometric properties of this Y, this I-card cubic fourfold. So first, it always passes through this point 0, 0, 0, 0, 1. And this one we call it I-card point. And secondly, so in this equation, if I set L equals 0, then automatically F equals 0, and X5 can be anything. So in other words, this smooth cubic fourfold contains a cone. The vertex is this I-card point. Actually, that's why we call it I-card point. And the base is some cubic surface. So it's this X intersect with H. And of course, finally, from the equation, you can see that this Y means involution, which sends this new variable X5 to negative X5. And this involution fixes P and also fixes a hyperplane, which is X5 equals 0. Okay. So then for this cubic threefold pairs, we associate a cubic this I-card cubic fourfold Y to it. This is a picture on its geometric on these three geometric properties. So it has this I-card point. It contains a cone over a cubic surface. So then geometrically, on this cubic surface, this X intersect H. We have this 27 lines in certain configuration, and this 27 lines will give us 27 planes, all passing through this I-card point P in this cubic fourfold Y. And of course, these planes will also be in certain configuration. So in other words, we can see that this I-card cubic fourfold Y is a lattice polarized cubic fourfold, which is similar to this lattice polarized K3 surfaces. So then we can define a period map from the moduli of this cos moduli of this cubic threefold pairs to some period domain, actually type 4 period domain or K3 type period domain. So what we do is we have this cubic threefold pair. Then we basically consider the Hodge structure on this on the middle cohomology of the cubic fourfold. But because it's it always contains some algebraic class which form a lattice So I mean, we call the lattice M. Sorry, I forgot to mention. So the H31 part or the Hodge structure can only be in the orthogonal complement of this lattice. So anyway, so basically here we take the Hodge structure on the transcendental part or on the anti-invariant part equivalently. So that gives us a period map. And the result joined with Radulada and Greg Pelstein is that this period map P. So this guy is injective, and we sort of we also describe the image, and this one we also prove that this period map extends to an isomorphism on some GIT compactification, and some Bailey-Borel compactification of the corresponding period domain. Okay, so this is what we did for these cubical threefold pairs. Okay, so we first encode them as a cubical fourfold, then use some Hodge theory for cubical fourfold. Okay, and then now let me talk about what happens for these cubical surface pairs.
Can I ask a question?
Yeah, sure, please.
So this GIT of
yeah.
Is a GIT of surface pairs or of threefold pairs?
Threefold pairs.
So it depends. Yeah. You have a choice of
slope. Yes.
Yeah, and the choice is 1/3.
Yeah. Here for Bailey-Borel is 1/3. Yeah.
Okay.
Thanks. That's a very important point in our paper. Mm-hmm. Okay. Let me continue. Okay, so then this idea for starting this cubical surface pairs, like a one-dimensional lower, is quite similar with like the construction is quite similar with the construction before. So specifically, I mean, we have a cubical surface, we have a plane. Let's say the equations are given by F equals 0 and L equals 0. F is a cubical form, L is a linear form. So then we also associate a cubical threefold X to such a pair. I mean, the equation is of the same form. So we call it I-card cubical threefold because essentially because it contains a cone. So this guy is also smooth. But I mean, as I said before, if you let L equals 0, F has to be 0 and X4 can be anything. So in that way, you can see that this X contains a cone. The vertex is just this I-card point P. And the base is basically F intersect L, which is a smoothly elliptic curve. And okay, and of course, this X also meets involution, which sends this new variable X4 to negative X4, and it fixes a point P, this I-card point P and the complement hyperplane X4 equals 0. Okay, and in the rest of the talk, I will keep using these notations like PE, tau, S, and pi. Okay, and so then like towards our results, so we try to define a period map by consider the Hodges by using the Hodges theory for this cubical threefold. So so I mean okay, so it will we define this period map from the moduli of these cubical surface pairs to some modular space. So what we do is we have this cubical surface pair as pi. So then I look at X. I consider the intermediate Jacobian of this X, and the involution tau induce an involution on this intermediate Jacobian. So this Jx is just the intermediate Jacobian of the cubical threefold. Okay, and then we define this invariant part and anti-invariant part by taking some by taking the image of 1 plus tau and the image of 1 minus tau. So this is actually a pretty standard thing to do to whatever decompose a Abelian variety. And then the principal polarization on this intermediate Jacobian on this JX induce a polarization on the invariant part and on the anti-invariant part. So on the invariant part, okay, yeah, probably I should say that, sorry. So this guy has a dimension 1. Dimension 1. This guy has a dimension 4 by some standard computation. And the principal polarization on the intermediate Jacobian essentially induce a principal polarization on this invariant part, or more precisely, twice of the principal polarization. But on the anti-invariant part, it induces a polarization of type 1112. That's also some standard computation in the theory of abelian varieties. So then this target, this A41112 simply means the polarized abelian variety, like a pair of abelian variety and and the polarization, but the type of the polarization is 1112. So then we have this period map. Okay. Is this clear? Okay. And okay. And this graph is this picture is just to illustrate the geometry. So yeah, sorry, I should say it before this the definition of the period map. So we have this Eckhart cubic threefold X. It has an involution tau. So tau fix this green point, the Eckhart point, and the blue hyperplane. And this hyperplane section is actually the cubic surface. And then we have this cone. The cone is only over this elliptic curve. And okay. And in what follows, we will always view this elliptic curve and this cubic surface as in this hyperplane. Okay, that's that. And then let me state our results. Basically, we proved 2 theorems. The first theorem is about the Torelli theorem. So we proved that this period map defined in the previous page. So this period map. So it's injective, and it has injective differentials. Okay. So namely, we proved some global Torelli and some infinitesimal Torelli. So actually, the proof of this infinitesimal Torelli, to prove this infinitesimal Torelli, you only, I mean, it's pretty standard, involves some pretty standard infinitesimal Haughey theoretical computation. So in this talk, let me only focus on the global Torelli part, like this map is injective. And to prove this, this map is injective, there are kind of 2 ingredients. So the first ingredient is that we proved that this anti-invariant part defined here. Defined here. So this guy is isomorphic to the dual abelian variety of some prime. Okay. So later I'll explain what is C and C tilde, but here let me just say that this involves a double curve of a plane quartic. So C is a plane quartic, and C tilde is the double curve of this plane quartic branch at 4 points. So yeah, in the next page you will see that we have some corresponding moduli for this plane, and also second key ingredient is some theorem on the fiber of some plane map stated here. Okay, so that's our second result. So here, let's say X and P is the Eckhart cubic threefold. So we consider this plane map, which naturally arises when we study the anti-invariant part of the intermediate Jacobi. So this one basically sends a double curve of genus 3 curve branch at 4 points to some abelian fourfold with some polarization. And so now if I have Eckhart cubic threefold, this anti-invariant part, or the dual of the anti-invariant part, will live here in the target. And our second theorem is that this fiber is isomorphic to the elliptic curve, which is which is this which is just the original cubic surface intersect with a plane. Okay, right. So from this cubic surface pair, we construct this Eckhart cubic threefold, and this elliptic curve is simply the intersection of this cubic surface and the plane. Okay. Okay. So here, let me okay. So so here maybe let me say two things. So okay. So one thing is about some allowable covers. Okay. So here we can not only consider Ital covers of smooth curves. For some reasons, we have to consider some nice degeneration of these double covers, which the terminology in Donaghy-Smith is allowable. So I'll explain it in the next page. And also let me briefly explain why, what's the relevance of this elliptic curve with the fiber here. So basically, this elliptic curve, it will parameterize some invariant lines for the involution. And I mean, a standard thing to do to study the geometry of cubic threefold is you pick a line and you project the cubic threefold from that line to a complement plane to realize your intermediate Jacobian as a plane. Okay. But anyway, so we'll see more details later. Okay. So now let me explain what do we mean by allowable. Okay. So here, by allowable branched double cover of stable curves, we mean it means two conditions. So first is the miserable, namely, okay. So let's look at this diagram. So suppose I have a branched double cover of stable curves d tilde to d, and the covering involution is iota. I mean, or the miserable means the fixed points of iota are nodes. And at every node, the branch are fixed. Okay, but anyway, I mean, we can simply think like these are some relatively nice degenerations of Ital double covers. Okay, and the second condition is that the number of irreducible components exchanged by this iota is the number of nodes exchanged by iota. And this it basically implies that even if we are talking about double covers of singular curves, we can still take a prime or generalize the prime. In general, this generalized prime will be a semi-abelian variety, but lovable, I mean, you can see, but if the double cover is lovable, then this prime will be compact. So we do get a map from this, this prime map do send some double covers of singular curves to this compact abelian fourfold with certain polarization. Okay, and okay, so finally, let me say that why we have to consider is lovable double covers. That's because when we project the cubic threefold from a line, generically we get a very nice stuff like double covers of smooth curves. But sometimes if the line, I mean, is not in a generic position, we could get some double covers between stable curves. But these double covers cannot be too bad, so they will always be allowable. Okay. That's that. And okay. Hopefully the statement of the theorem is clear. And then let me make a couple of more remarks. So one remark is that theorem 2 is about the positive dimensional fiber of some prime map. And it's similar to the following theorem by Donaghy and Smith. So in 81, Donaghy and Smith proved that if I have a smooth cubic threefold X, and I consider this a proper prime map, which sends a double cover of genus 6 curve I mean, this is a prime map. So we have a double cover of some general 6 curve, and we send it to the, we take the prime, and the prime will be a compact PPAV of dimension 5. Okay, Donaghy Smith proved that the intermediate Jacobian or the fiber of this prime map of this intermediate Jacobian is isomorphic to the final surface of lens. So the idea is here you have a cubic threefold X, and you just take a different lens on this cubic threefold and try to project your X from this different lens. So then you get different elements in different double covers in R6, but the prime are all isomorphic to the intermediate Jacobi. Okay. So actually later we'll use Donaghy and Smith's strategy to prove theorem 2. And this is a quick comparison. Okay. So in Donaghy Smith, so they look at, they consider this prime map P6. And we basically consider the anti-invariant part for this I-card cubic threefold. So it's a P3-4. So this P6, Donaghy Smith proved that it's proper dominant generically finite of degree 27. And by some result of okay, so and this P3-4, so it turns out to be proper dominant generic finite of degree 3. It's a result of the I cite the reference here. Okay, and so later I'll give a illustration like why this P6 is of degree 27. So that basically boils down to the geometric effect, like a general or smooth cubic surface contains 27 lines. And our theorem 2, it might be of independent result. So I think from the theorem 2, we gave a geometric interpretation of this result, like why P3-4 is of degree 3. So so later it will correspond to the geometric effect that if I take an I-card cubic surface, which means a cubic surface, like the equation is just the F plus L, F plus L times X3 squared. So this is a classical object of study. Okay, so this guy also, this I-card cubic surface also has an involution, and the involution will fix 3 lines. And yeah, so so I think this 3 gives a geometric interpretation of the theorem here. Okay. 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 So that's basically our results. Are there any questions? Okay. If not, so maybe then let me go to a bit more yeah, details. Okay. Okay. So so then let me try to explain how do we obtain these results. So okay, the basic idea is how do we try to study this intermediate Jacobian of cubic threefold? We just try to project this cubic threefold from some line, try to realize this intermediate Jacobian as primes. Okay, let me quickly recall here that okay, so if I have a smooth cubic threefold, I have a line, I can project this cubic threefold from a line, and then I get some conic bundle. So so here are some pictures. So okay, so this is like L. So if you project, you get some cubic curve. Generically, it's a line plus a conic, but at some point it will become a union of 3 lines, or a double line union this line, and on the complement P2 here, there will be a quintic curve parameterizing these degenerate fibers. We will call them discriminant curve. Okay. And generically this D will be smooth, but if the line is in bad position, could be stable. Okay. And then what is D tilde? D tilde is basically the union of these two lines. And the covering involution is, you exchange these two lines. So that gives us a double cover of this quantic curve. Generically, it's tau connected, but it could get singular, or in other words, we have to consider some lovable double covers. Okay. And then it's a classical theorem of Clemens, Greenfield, Mumford, and in the allowable case by Beauvais that the intermediate Jacobian is just the prime of this double cover of the discriminant quantic. Okay, and so that's what happens for any smooth cubic threefold. And here we have Eckhart X, so it has an involution. So to study this intermediate Jacobian and how the involution decomposes the intermediate Jacobian. So okay, so here what we do is we try to project X from an invariant line to some invariant complement plane. Okay, so the first thing we have to do is to classify invariant lines in Eckhart cubic threefold. And it turns out that there are two types of invariant lines. So there are 27 lines contained in the cubic surface, and then there are a pencil of lines passing through the Eckhart point. The Eckhart point parameterizing by this elliptic curve, like contained in the cone. So here is a picture. So suppose I have invariant line L. So okay, so it's either in this cubic surface, contained in the cubic surface, or it will, form the ruling of this cone, or in other words, or it will pass through the Eckhart point, and joining this Eckhart point and some point on the elliptic curve. Okay. It's actually very easy to prove. But anyway, let's continue from here. So then let's try to project this Eckhart from these two types of lines. Okay, so if I project it from one of the 27 lines on the cubic surface, then the way I can see this actual, okay, so then I'll get some actual involution. Let me explain. So generic, for any cubic threefold, you will always get this cover. So D is a discriminant quantic, as we just explained, and this D tilde is just the union of two lines. But now because this X has an actual involution, so when I project from this pointwise fixed line, this D tilde not only has a cover involution, exchange these two lines, but also has some actual involution coming from the Eckhart involution. Okay, so in this way we get some curve with a Clevin 4 group contained in the automorphism group, and we get this tower. And this is quite similar with I think what Mumford did for hyperelliptic primes. But anyway, so then by studying this tower carefully, we prove that the invariant part is essentially the elliptic curve, and the anti-invariant part is isogenous to some prime. And we describe the fiber, the kernel explicitly. But this description turns out to be turns out that we don't need this description for theorem 2. So let me so we can let me just mention in the rest of the talk we won't need this. Okay, so what will be crucial for theorem 2 is what happens when we project this Eckhart from a line on the cone or a line passing through the Eckhart point. So always this P, this small p means the Eckhart point. Okay. So there, the special thing is that my discriminant curve splits into two components. Okay, so actually it will split as a plane quintic C and a line. Okay. So maybe let's look at this picture. So generically, if I have a smooth cubic threefold, I project from a line, I will get a smooth quintic. But for this I-card and for this type of invariant line, I get a quartic, sorry, a degree 4 curve, a quartic and a line. And one way to think of that is, so where does this quartic come from? Okay. Okay, so okay, so here I take a line joining the I-card and one point on the elliptic curve. So this point is on the cubic surface. So basically, the way, the reason why we get this blue quartic curve is I just project my cubic surface from this point. So in that way, I mean, by some classical algebraic geometry, if you project a cubic surface from a point, you get a double curve of P2 branch along some quartic curve. Okay. But of course, you need to do a flow down to get the cubic surface back. But okay. Okay. So anyway, so this we get this quartic kind of naturally. Because of we have a cubic surface. Okay. And then this line component also arise naturally from this plane. Okay. So remember the cubic surface pair consists of S and pi. But now we sort of get we do some projection simultaneously and get a quartic coming from the cubic surface and get a line coming from this plane pi. Okay, and in this case, we proved that the invariant part is again isomorphic to the elliptic curve. Okay. And let me say that this elliptic curve is exactly the intersection of S with pi. And the anti-invariant part, so this is what we will be using later. So it's just the dual abelian variety of this prime of this natural double cover restricted to the quartic part. And okay, so here actually the proof was based on some discussion with Julia Saka, and it was also a starting point of this project. Okay, so here maybe let me not go to details. Let me just say that so here the kind of K ingredient is a description of this prime variety due to Beauvais. Okay. But okay. But anyway, so here we get my discriminant quintic splits, and I can see the invariant and anti-invariant part from the these two components. Okay, so then let me try to explain how do we prove this theorem 2. Okay, so remember theorem 2 is about the fiber of this prime map. Okay. Okay, so let's start with the following observation. So remember we have two types of invariant lines. The second type of invariant lines always passes through this I-card point P. But I mean, we have a lot of choices. If I choose different lines, I project from these different lines, I will always get you know, my quintic will always split. So I can always restrict to the quartic component and get some double covers in this R34. So some double covers of genus 3 curve quartic branched along 4 points. So okay, but there, I mean, as we proved, the prime of these double covers will all isomorphic to the anti-invariant part. Okay. So in other words, so here if I consider what is a fiber of this anti-invariant part, it's kind of easy to show that this elliptic curve, if I think of them as type 2 lines, invariant lines, or invariant lines passing through the Eckhart point. So it's kind of easy to show that this E is contained in the fiber. So actually, by some infinitesimal computation, like by studying some differential of the period of this prime map, you can show it's a connected component, blah, blah, anyway. Okay. So then to prove theorem 2, the difficult part is we have to show that this E is a whole component, like no other components. I mean, just to give some idea of the proof. So this is a key kind of the key point. And what we do with Yano is we use some local degree computation. This idea contained in the paper by Donaghy and Smith to prove that there will be no other components. So then essentially we are done. Okay. So this is the local, essentially the local degree computation idea contained in Donaghy and Smith, and we rephrase it so that it works better in our situation. So here, of course, it's kind of technical, but let's say that let me briefly explain. So let's say we have a proper surjective generic finite degree map F. In our case, it will be some pre-map. And let's take some subvariety Z in Y and take the fiber of this Z. Okay. So then if I have a component Z0 tilde of this fiber, okay, I mean, we are in this situation, right? So this is a fiber and this is some component of the fiber over Z. Okay. And now, for example, I tried under some assumptions, technical assumptions, I try to prove that this Z0 prime is actually the whole fiber over Z. Okay. So what I can do is I can try to take advantage of this degree. Okay. But here you may have positive dimensional fibers. So automatically we cannot talk about the degree here. So the idea of Donaghy and Smith is that they try to blow up Y along Z and blow up Y prime along Z0 prime, so that this will become exceptional dividers. Okay. Okay. And here, sorry, I forgot to say. I mean, in all the let's say this Y prime and Y has the same dimension. Okay. And then under some assumptions like this Z0 prime dominant this, after I blow up and I restrict it to exceptional dividers, I mean, I get a map, a finite map, and I can talk about a finite rational map for which I can talk about the degree. So then Donaghy and Smith essentially prove that if the degree of the original map equals the degree of this between these two exceptional dividers, then this connected component Z0 prime will be the whole fiber over Z. Yeah, of course, it's more technical. Like we have to assume Y is normal, so on and so forth. But I guess the basic idea is to blow up and restrict to exceptional dividers to compute the degree from positive dimensional fibers, and I think this is the basic strategy, like how Donaghy and Smith prove like the pre-map is of degree 27. Okay. but then we basically use this strategy to prove our result, to prove that there can be no other component. But let me illustrate this idea, by proving the following theorem by Donaghy and Smith, and explain what we need to modify in our case, in the Eckhart case. So this theorem I mentioned it before. Let me remind you again. So if I have a smooth cubical threefold, its intermediate Jacobian will be in this A5. Then I also have some pre-map from this double curve of general 6 curves to A5. So the theorem says that the fiber over its JX is isomorphic to final surface of length, which is essentially corresponding to you choose different lines in X and you project from this different lines. Okay. And so let me give a very quick sketch of the proof. So this is a map we are interested in, right? So this P6, this pre-map. And Donaghy Smith already proved its degree. The degree is 27. Okay. And now I take the moduli of smooth cubical threefolds C, okay, or more precisely take their intermediate Jacobians. And then I take the fiber over its C. On the other hand, so if I choose different lines on the cubical threefold, I project from these different lines, I get I get some double covers of plane quintics. So this will become a connected component of this fiber, and the fiber of this map at every X will be this final surface of length. Okay, and then the goal is to prove that these two are the same. Okay, yeah, sorry, it's rather technical, and I just try to give some ideas. Okay, so then what we have to do is we need to look at the blow up. We need to blow up this stuff and look at the map between the exceptional dividers. Okay, and these exceptional dividers are just a projectilization of normal bundles. So this map is essentially the projectilization of the differential map restricted to the normal bundles. Okay, so then in Donaghy and Smith, or to compute this local degree, the key step is to compute this degree. We need to do some infinitesimal computation. For example, compute this differential of the period map. Okay, so then let's consider this diagram. Okay, and this is not a fiber product; it's just a commutative diagram. And let's say we take a line in the cubical threefold, and which gives me a double cover of the discriminant curve. And for simplicity, let's say we are in the very good at a good point. So the discriminant curve is smooth. The cover is E tau. Okay. And let's assume the quintic is given by Q equals 0, and the cubical threefold is given by F equals 0. So then you basically take differentials of this diagram, or they're like the co-differentials, or like the cotangent space everywhere. Okay, and there are a lot of identifications, but the map we are really interested in is kind of this map between. So these are just the conormal bundles. Conormal bundles. In a smooth case, we can identify them with some using some Jacobian rings, or Jacobian ideals. I'm sorry. Okay. And write everything in a fairly explicit way. And then the map between the exceptional dividers will be the projectilization of the dual of this map. And okay, and at the end of the day, after a lot of identifications, the map is simply it's simply this from this P2L dual into P4 dual. So let me explain. So this P2L dual are all the hyperplanes contain this line, and I just send it to the hyperplane, which is parameterized by this P4 dual. Okay, anyway, so let's say the upshot is that then if I look at the map between the finite map between these exceptional dividers, so here I can think of a point on the exceptional divisor C tilde. You basically just blow up whatever A5 along this the locus of intermediate Jacobians. So I can think of them as pairs like X, cubic threefold, and hyperplane. Okay. And now which point lies over this guy? So it corresponds. I mean, the point will be some plane quintics. So which further corresponds to some lines on the cubic threefold. Okay. So now, by this lines. So first, this line has to be in X, and secondly, by this identification. So this line has to be contained in H. Okay. So now we are basically counting how many lines are there, are contained in the intersection of X with H, which is a cubic surface. So generically, because a cubic surface contains 27 lines, so the local degree here is 27, which is a global degree. So then we are done. Okay. That's sort of the idea. Okay. So then let me go to the proof of theorem 2, which is on the Icard case. Okay, so basically we try to prove that the fiber contains no other component other than this elliptic curve, which parameterizes some invariant lines. So starting point is of course this guy by some previous results. So it has degree 3, okay, and we use exactly the same strategy. And here let me just say that the strategy is the same as in Donaghy-Smith, but there are some difficulties. Like the modification we have to do is first we have to go to the boundary case of Donaghy and Smith, because like our discriminant curve, it will be a line union of plane quartic, so it will be a lovable cover, singular cover. So we have to do some deformation theory for this singular or this lovable covers. And also we have to keep track of the involution, but that's kind of the natural thing to do. Okay. So anyway, so then it will become more technical, and let's not worry too much about that. And but at the end of the day, we can identify this the map between exceptional dividers as follows. So for this C, so epsilon means the Icard, right? So for this CE tilde, we can think of them as the Icard cubic threefold together with a plane which is passing through the Icard point. So it's an invariant plane. So we did some similar computation as here and prove this result. Okay. Okay, and then here, I mean, we are choosing invariant lines passing through the Icard point. But also we have to make sure that this lines is also contained in this plane, this invariant plane. So then geometrically, we are asking, like, I have Icard, I cut out this Icard threefold by a plane passing through the Icard point. Then I get this classical Icard cubic surface. Then how many invariant lines are there? So the answer is 3. Is some classical result on this Icard cubic surface. But this 3 is the global degree. So essentially we are done. Okay. Okay. And finally, let me quickly say something about how do I use the fiber of the pre-map to prove the Torelli theorem, the global Torelli theorem. So the key point is that, so now suppose the two Eckhart cubic threefold has the isomorphic anti-invariant part. The key point is that, okay, so then like their prime are isomorphic to each other after taking some dual. But then by the fiber of, by the fiber of the prime map, I mean, we know the fiber, right? So it's an elliptic curve. So if these two things are isomorphic to each other, that means basically we're just choosing different lines. So anyway, so then we can realize the other prime on on this x0, but using a different line. Okay, I guess that's a point. Then after some you have to do some more argument, but essentially that tells that's like the key point for proving this theorem. Okay, so maybe let me stop here. Yeah, thank you.
Thank you.
Yeah.
Okay, we have some very little time for questions, but maybe some. So I'll open the floor. If anyone wants to ask a question, please ask now. I stop the video recording.